just doing a dramatic reading of it to get through that in an hour. But there's nothing more boring than listening to anybody who's not only getting back about proofs. It's also a theoretical result, and that often carries with it a little bit of a reticence to engage, because I imagine, actually, is anybody here, how many people here are in Wisconsin academia who goes to university as a day job? A couple of people, right? So as I predicted, most people here are expected practitioners. Your day job involves actually writing code rather than maybe thinking very, 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 very hard about it. And yet I want to talk to you about theoretical results. So I need to justify that. It's an extraordinarily impactful paper. Referenced everywhere. Really shows a quite surprising result. They even note in the paper themselves that actually this result, you cannot do consensus. If one process is halted, it's actually a bit surprising. And it settled a number of practical questions. And there are many practical applications that have become only more relevant in the past 10 years or so about why and how consensus might be useful for systems that we actually build. And I'll try and motivate that as we go through the talk. It's also true that this, I believe I'm right in saying I'm not a historian, but I believe this gave rise to a great, very profound, interesting set of academic research about what really is possible in communication networks where you can leave messages or messages in the order, but things may fail. And it turns out consensus is a really fundamental problem to study in that area. And personally speaking, and it's a paper that I am quite fond of, it's a paper I read maybe 7 or 8 years ago, 2006, 7 years ago. It brought together a number of intuitions I felt I had, but really didn't have the experience or the time to articulate properly. The way that they, in this paper, rely on very fundamental things like failure, like asynchronicity, like the only way to coordinate is through messages. These are all ways that, or ideas that gave me the ability to form a framework for about distributed systems. So I hope I can do this paper on system justice. It was a Dijkstra award in 2001. You actually want to read some of the best distributed systems papers, at least theoretical distributed systems papers. Go and look at most of the Dijkstra award winners. They're all, they take a long time to get through because they're all quite profound and quite beautiful. What I want to do today, excuse me, is I do want to walk through the proof. I mean, it's a paper that proves something. And so I wouldn't be doing it justice if I didn't actually walk through the steps required. So that's going to get a little hairy. I mean, it's not an easy thing to follow. It's not an easy proof. I'm going to make a couple of shortcuts. I'm not necessarily going to tell you where they are. But I hope I can leave you with more than an intuition about why the proof actually works. And as I say, I want to show you how this paper may give rise to some kind of framework for thinking about it. The other frameworks are available, but I like the way this encourages. If you either of these two things are honestly feel like it's successful, they can both be good enough. So let's start with consensus, and just want to lay a little groundwork really to establish a common frame of reference of what we're actually talking about, which is consensus right there in the title. What do I actually mean by this? And you hear consensus as a word bandied around a lot, especially if you're people like me who spend a lot of time reading 140 characters on Twitter. People talk about consensus really as a proxy for hard distributed systems problem. They establish a binary. There are people who understand and can implement consensus, and there are people who can't. And that's how I decided to do it. I think it's crap. Consensus is a problem, particularly in the situation of Paxos, is gaining kind of fearsome reputation that I don't think is necessarily fully deserved. It is hard to get consensus right. It's a difficult engineering problem, and smart people work quite hard on it. But to understand the problem of consensus is not so difficult, not so hard. And hopefully, if this is a new problem to you, to know this, then it should be, hopefully it should be enlightening. So what is consensus? Really broadly, I mean, there are many ways to take it, as I tried to be as clear as I could here. Consensus is the problem of having some set of processes agree on a value proposed by one of those processes. But actually, there's a number of subtleties embedded within this definition. What's a value? What does it mean to propose? What does it mean to agree? These are all things that you can make concrete really by establishing a set of rules that any protocol that can solve the consensus problem, i.e. cause some processes to agree, some set of rules that that protocol has to adhere to be valid. And so these are the three rules that are typically agreed upon in the literature. It's actually true that this formulation doesn't appear anywhere in the FLP paper. It's the standard way of describing the problem nowadays. There are three things you must do. If you are a protocol and you solve consensus, what must you do? It must be valid. That is, if you agree upon some value, it means that some process in the system must have originally said, I think this is the value we should agree on. The reason this is important to observe is that otherwise you can have a trivial consensus protocol that says, look, we're always going to agree on the value X. Nobody needs to actually think too hard about this. We don't need to exchange any messages. We don't need to communicate. X is what it shall be and shall be forevermore. That's a really uninteresting problem. So to keep it interesting, you have this validity property. There's also this notion of termination. So the formulation in the FLP group is extremely weak, which says that only one process in the system, that's one non-faulty process, has to eventually decide. More general consensus protocols often say, well, actually, I really kind of would like it if every node in the system, like the database here, I kind of would like it if every node in the system agreed upon this value, at least some majority of it. But consensus itself, as opposed to, you're only going to get one process past the finishing line. Only one of them has to agree. And then finally, we've got this idea of agreement, which seems kind of important. If more than one process decides, they all have to decide on the same value. There's nothing particularly profound about that, but it seems an important property. If we're all agreeing about who the next leader of the system is, well, we should probably do that. For the purposes of this discussion, the presentation is vastly simplified by only allowing one or two values, 0 or 1. You'll see as we get really into the woods with the proof, having more values would really, really complicate the presentation to no good end. But understanding we can generalize from 0 and 1 to next state should be X, or next leader should be this node, or you should commit this transaction. So these three properties, it's always worth with the system's problem, analyzing the properties that you want to maintain in terms of both safety and liveness. There's a paper whose reference I couldn't dig up, unfortunately. I read it back in grad school a long time ago. It says, all interesting properties of distributed systems can be posed as a combination of both safety and liveness. Now, to thus, a safety property is one where you say something good. Like, I always get it confusing. A safety property. Yeah, let's start with liveness. Okay. A liveness property is one where it says eventually something good happens. A safety property says nothing bad happens. So these are subtly different, they're not quite the converse of each other. So the middle one, termination, at least one non-faulty process eventually decides. That's a liveness property. The process will stay alive, something will eventually happen. It shows that the protocol is actually working. The other two properties are safety properties, which is to say if they're violated, then something bad has happened. Which is to say if we agree upon a non-proposed value that violates this property. It is now a safety property, it is violating the unsafe, incorrect. So this is how we think about consensus abstractly, theoretically. To think about it in real systems, why is it an important problem? So I've got three demonstrations here. Details are lighted, as you might imagine, but let's imagine we're a database and we want to commit a transaction. You might propose, should I commit the transaction? Yes or no? Then you have in the middle this box that says, well, I have a magic consensus protocol, and we'll establish why that's a tricky thing to do a little bit later. And the outcome of that is either yes, you have agreed upon this value of yes, the proposed value of the system, or some other node in the system might propose the value no, I don't think this is a good idea to commit the transaction. It conflicts with something that I have already committed. It's a very terrible idea. The transactional commit. incredibly important in databases can be framed as an instance of the consensus pair. So can this idea, which is very similar, of replicated state machines. So a replicated state machine is a way of having many nodes in a distributed system act like they are all. You're right over there, brother. Replicated state machines are a way of having a distributed system. Many nodes act as though they are all simulating the same state. So node 1, node 2, and node 3 in the system are moving in lockstep. They might be replicating a list data structure, let's say, or queue, or they may be something much more complicated, like the number of stated locks that have been taken in your distributed lock service. The idea is that you replicate that state out in order amongst these nodes so that you have some degree of fault tolerance. So if node 3 fail, on node 1 and node 2 are there, and you can guarantee the application of our consensus protocol that node 1 and node 2 have got the same state. So the way that works is the client maybe proposes that the next state of the system should be S, and then we have, again, our magic consensus protocol, which is taken out, and then we have...
we'll bring it here, yeah. Yes.
And then the consensus protocol agrees, and so, okay, well, let's say the new state is written to the lock. You can see that state S and block N is replicated in 3 ways. Final example I have, I tried to do something topical, but given that I had a trial topical in about 2012, so the leader election in the context of the 2012 presidential election in the United States. It's the leader, someone proposes, well, there are 2 values proposed by the system now. Then you have a large set of people executing a magic consensus protocol. And finally, only one of them actually becomes president of the United States. So you can see that this property of agreement is very important here. If only actually believed that he was the president of the United States, you'd have some kind of conflict, at least in 2 chairs in the Oval Office. Kind of so leader election, again, another system that requires a consensus protocol to do presidency. And so require a benefit and a consensus protocol to do in a strong way where there's only one leader elected at any time. So that's kind of a very quick overview of consensus. That's 3 reasons it's useful in distributed systems. Let's talk about the paper in a little more detail. So, what does FLP actually say? Now, I think it's best to explain this perhaps by analogy with the cat theorem, which I'm sure you're heard of because you're alive today. People will tell you about the cat theorem if you walk past another street. And the cat theorem, of course, says that you can't be consistent, available, or suffer partitions in the asynchronous network at the same time. So, by analogy, we have Fischer, we have Nancy Lynch, we have Mike Patterson, so Fischer and Patterson. FLP says that you can choose 2 of them. You can only be 2 of them at any one time. The proof left is an exercise to the reader. Really, I'm being facetious. Although, I just want to take a pause to kind of eulogize slightly Nancy Lynch, who seems to have done so much of the most important work in distributed algorithms over the past few years, all the students. She, in my opinion, should be nailed on for a Turing Award that we will wait and see what she gets that. That said, do not try to read her book, Distributed Algorithms. It is not prose to stir the soul. It's rather dry. But she's actually, her papers are fundamental and particularly important. 3 of them she's come up with particularly giant in the field. What does FLP realize? Okay, so distributed consensus, restated, rephrased what we tried to say here. Distributed consensus is possible that at least one process might fail. So this is, as I say in the paper, it's a surprising result. And I believe what's surprising about it is particularly one process might fail. You can imagine distributed consensus is difficult if lots of processes fail. But for the fact that just one process torpedoes the whole affair is to me that it's surprising. Let's pull this apart. The first word that's important is distributed, and for our purposes that means a message passing network. There's no shared memory. We'll talk a little bit more about this after the session, but there's no other way of coordinating amongst processes in the system other than sending a message. And this is very important. Consensus, we've talked about, so consensus in the sense of must be a protocol that finishes, where it actually does the right thing, and everybody agrees on what that right thing is. Is what's the approach, we're probably comfortable with that. But impossible is a really interesting term. So I want to key on this word a little bit because the original the cat videos, of which there were very few survivors, showed that people react strongly to the idea of impossibility. Often judging it means something much wider than it actually does. I'm sure you guys are precisely meaning the probably obvious that I don't put it is important. We say a problem like consensus is impossible to solve if there is no algorithm that works correctly in every circumstance. And by circumstance, I mean parameterizing over all possible sizes of cluster, all possible interleavings of message delivery, and all possible patterns of failure in the system. All you have to have is one situation where your consensus protocol did not do the right thing, did not meet one of the termination, validity, and agreement properties, for us to say, oh, sorry, that protocol doesn't work. So when we say this is impossible, we simply say that every protocol, every algorithm you come up with, you think solves consensus, has an Achilles heel, has some execution environment in which you just couldn't do the right thing, and we're really sorry about that, but that's what the fundamental theorem says. So one thing we'll talk about maybe quite a lot later is you can manage the circumstances under which consensus can't be used. That's a key to making this result practical. If you can actually go some way to saying, okay, I know it's not going to work in a couple of circumstances, but I'm going to engineer my system in such a way as to make the probability of those vanishingly small, then you start to actually responsibly engineer around this impossibility. So moving on, the last thing that's interesting here is at least one process might fail. Now, if you've read the systems papers, you'll know that fail is a very overloaded term. It actually means several things. Getting or becoming precise about what failure means for a particular problem is often the key to a problem being solvable or impossible. And so I just want to, here we mean crash failures. And by crash failures, I mean some process in the system just stops dealing, just goes to sleep and never wakes up, doesn't send any messages, doesn't take any steps, just says, screw you guys, no. That actually is a very limited failure mode. There's a hierarchy of failure modes. I'm going to present a subset of it. There are lots of failure modes. Crash failures, you can kind of put in the middle. Fail by stopping. Process is just, that failure mode is subsumed by this failure mode called emission failures, which is where the cat theorem actually operates. And that's fail by dropping messages. So that sounds like a network partition. You should be familiar with build up network partitions. Emission failures, all crash failures look like emission failures, but emission failures don't necessarily look like crash failures. And if you go one further up, on the outside, you've got this idea of Byzantine failures, which is just the process says, hey, screw you, send this message, I'm going to set this house on fire, I'm going to run a million miles an hour, and then I'm going to send everybody a message and get it all stupid. Byzantine failures, you can do whatever you want. And it's actually kind of interesting to me that Byzantine failures seem to be studied earlier on. If you look at the chronology, Leslie Lamport is doing his work on the Byzantine generals problem. Before FLP came out, before they had their paper. I suppose it makes sense that studying the most general kind of failure model before you actually know that even a very specific failure model like crash failures, you can't even solve consensus here, so you're absolutely screwed all the way up here because all crash failures could be Byzantine failures. So if you can't solve consensus for crash failures, you're really kind of screwed. So I want to show you this chart to show you how surprising it is that consensus, even with a weak failure model that doesn't allow for many of the kind of faults you might usually see in a predicated systems. Even not allowing for those, consensus is still impossible. So just to finish up kind of the description of the problem itself, you can't talk about what is my in this slide. It's not involved with system. What it means here is you have the possibility, your system allows the possibility of at least one failure. You could actually bound it. You can say it doesn't allow more than 3 failures. And then you would only have only 3 processes you might fail. Doesn't mean that they fail in every execution. But actually, as we shall see, it's that possibility of failure, and quite deeply the inability to distinguish that failure from a node that's just running slow that hasn't sent all its messages yet. It actually means that that's what throws a spanner in the works. That's the thing that's eventually taking further having to say, sorry, we really can't do this. Does that answer your question? Okay. Right, so let's skip on. It basically means you live in fear of failure. So more on the system model. A system model, and you absolutely have to know what a system model is, as I said before, in order to say anything reasonable about impossibility or possibility. And I view the system model as an abstraction you layer over messy computers that actually have a kind of annoying behaviors. You simplify those down and say, what's actually important about the property of this? So for our purposes, we've got the system. The only way that those communicate, as I said before, is by delivering messages to one another. And that means, for the purposes of this paper, then you send a message, and then at some time later, you do not know when, the message will be received by the person who sent it, unless that person is dead. So the messages themselves are never lost. If I send you, real time, if I send you like 1,000 UDP packets, you're going to get 1,000 UDP packets. But this being UDP, they may be delivered in any order. So you may get the 971st packet first, which can be really confusing to you unless you built in some way of dealing with that. But this actual ability to reorder messages is the kind of the other side of not being able to distinguish between slow processing and delivery. You cannot ever say, well, I haven't got that message I was expecting. Maybe he's failed, but maybe he's slow. I just don't know. And in order to make this more precise, one thing that's important is that nodes themselves, the processing system, do not have access to a shared code. So you can't do the neutral time acting. In 2 seconds, if I haven't got your mail, I will do this thing. Because I may know when 2 seconds is up, but you may completely disagree, because your clock is completely different. So you may be on GMT or on PST over here, and your clock is running twice the speed of mine. You have no way of making that accurate. So evidently, I made this point where it just reinforces there is no shared memory. Messages are the only way that nodes make order. So with that, context establishment. Let's start on the proof. Now, I made a choice, and it's a difficult thing to know how to do to prevent proof this complexity. Out of interest, and I don't mean to be ashamed, but how many people only scan the paper? You're all brilliant. Then you will have seen that the proof is not necessarily easy to regurgitate. It's not one of those incredibly elegant proofs where you just say, well, this, and therefore this, and then we all get home and calculate. There's steps in it. There are details. There are lemmas and things that should have been lemmas, but they don't actually say lemmas. And so as a result, it's going to be we'll get into some detail. Like I said, I'm going to cut a couple of corners. I'm going to miss out one lemma completely. I'm going to assert one thing's fact that I will not include. But do stop me if what I'm saying doesn't make sense. We're probably confusing as well, but we're likely to be confused both. Otherwise, I hope I will give you an idea of how to do this. Okay. So we need some definitions, unfortunately. So let's talk about the configuration. So a configuration is the state of all the nodes in the system at any one time. That's loosely defined, you can imagine this as a set of messages I received, whether or not I as a process feel that I have decided what my decision value is, and what the next thing I think I should do. The initial configuration is really the configuration of all the nodes in the system at time t is 0. And every node, we say, every process in the system has an idea of what it will propose. It has an idea of what it thinks the decision value. This will come out, this time out to be a very useful thing to talk about, the initial configuration. So process 1 says, I think it should be 0 until I get some messages and decide it. Okay. When we've got these ideas that sound vaguely like chemistry terms, states or configurations have a valency. And really what that means is a state is univalent if it's only possible to decide one value. No matter what messages you receive, no matter what happens, who fails, how long passes, etc., etc. You are, from a univalent state, you're always going to decide the same thing. So it may not mean that you've actually decided, it just means that the writing is on the wall, and you just don't know it. A bivalent state is instead one where either decision is actually possible. These are absolutely crucial, so asking you to explain them again if they're not 100% clear. The distinction between a univalent state and a bivalent state is completely fundamental to how the proof progresses. To be specific about univalent states, we use the phrase zero-valent and one-valent. A zero-valent state is one where you're going to decide 0. And a one-valent state is where you're going to decide 1. I will occasionally substitute the word decided and undecided, univalent and bivalent. I will try to not be confusing, but just treat them interchangeably. I think decided and undecided are easier to think of, but univalent and bivalent are what they say in the proof. So I want to sketch out very simply, 10,000 feet, how we're going to go about proving these things. So we hypothesize the existence of some initial undecided configuration. So the proof itself proceeds by really a kind of a proof by induction mechanism, which if you may or may not recall, maybe every day, I don't know. Proof by induction says establish a base case and then show that from any state that has property P, property state, the next state of the system will still have it. I'm not sure that actually helps. We hypothesize this initial undecided configuration. That's it. And then some messages get delivered, and we wind up in an undecided state. So, if the 10,000 system, this is what we are saying might happen. And then we say, well, okay, and once you get to that undecided state, some more messages might get delivered, the system might keep doing its thing, but you'll still wind up in an undecided state. And there are two lemmas that we're going to talk about today. The second lemma on the paper, lemma 2, says there's always an undecided initial configuration. Remember, I hypothesized it. Hypothesis is not proof. The lemma actually goes and proves that every protocol will have some initial configuration, i.e. kind of set it like what you think the decision value would be if you everybody gave them went out now. And that will always be undecided. Third lemma says, from that initial undecided configuration, you can always get to an undecided state. Because that's not immediately obvious as well. As the protocol continues to execute, you might say, well, in all executions, you might wind up in a decided state. That would be a correct consensus protocol. But the third lemma says, actually, there's always going to be some delivery order of messages. And remember, messages can be reordered. Some order in the message delivery is going to wind you up in an undecided state. And there you are due to state it out. So if you take away nothing else in the rest of the talk, take away this as the bare bones of the FLP. We show that you can start off undecided, and then there is some execution, some order of receiving messages that means you will stay undecided forever. So when we think about the three properties of consensus that we were talking about, termination, validity, agreement, it's clear that this violates termination. The system will never get to a decided state. If it doesn't do that, we can't say it's correct. Yeah, good.
One copy doesn't happen. Would it be fair to say that FLP set the instruction procedure for that incident
That is exactly right.
It's always going to build it for any unspecified consensus protocol. You might have this pocket. I can build infinite coverage.
That is exactly right, and I wish I'd spoken to you half an hour.
Can you repeat it because I missed?
Right. So hopefully I don't mangle this definition. A safety property, like the mutual agreement, has some finite counterexample. There's some bounded execution of the system. Receive these 10 messages. Oops, validity isn't satisfied. Same is true of agreement. But we're talking about their liveness property, and liveness properties have infinite counterexamples. You need to say that the thing you're waiting for is never going to happen. You're actually talking about affecting over. You're talking about infinite executions. All messages delivered forever. Processes take an infinite number of steps. And what this allows us to do, if you correctly observe, is we have a way of actually, it's not so much that we have a way of constructing the exact counterexample, but we show that one must exist. Not right. It's an interesting question as to whether you actually could, whether you could go that step further and say, okay, give me a consensus protocol and I will show you the trace that will be correct. That's not what's done. Yeah. I think that's bring program I can do something. Well, we're talking about a limited set of programs here. So I'm loath to say immediately, and I'd be a far better theoretician than I to say off the top of my head, oh yes, that's the equivalent protocol. I think you can have a generalized procedure for coming up with a counterexample. Given that we're showing, what we're showing here is that every protocol doesn't halt under some execution. Having done that is 90% of the way to solving some halting problem for consensus protocols. Now what we need to do is say, what's the actual execution? So, I mean, it's definitely true that you can't take this technique and apply it to all programs. That would be powerful indeed. So, another great thing people said, one thing beautiful about this is it's completely independent of any actual algorithm. So you may have about consensus protocols like Paxos or the Zuki Photonic Broadcast Protocol, Raft is doing a lot of some of those, let's say. But not only are we abstracting over the system model, we're abstracting over the idea of what it means to be a consensus protocol. We don't care what it does. We don't care what the Java flow looks like. We just know that it has to have these properties, and we're going to show you that it can't have all of them. So, level 2. This is what it says in the paper. Protocol P has a bivalent configuration. But we know now enough to say, we know what that means. A protocol must start must have some initial configuration. There's many initial configurations. Let's choose one, well, not choose one, but let us assert that one of them is bivalent, i.e., it depends on the messages you receive. It's not preordained what you're going to decide. If that weren't true, then we'd never get anywhere with this method of attack, because we would just say, well, it doesn't matter what messages you receive. It doesn't matter if the process fails. It doesn't matter what order things happen in. You basically just do whatever you like and then have everybody decide. That, of course, would solve consensus, but seems unlikely. So, really, the takeaway I feel from this matter is this idea that communication between nodes is important. And if you think about it, this is the base case now. This is the initial state. So let's imagine a two-node system. A two-node system with a possibility of deciding 0 or 1. So here we've got each yellow box represents a configuration. If you've got a two-node system, you can see that there must be 4 possible initial configurations. There are 2 values. So just to make sure that the notation is clear, C01 means that process 0 has 0 as its initial configuration, process 1 has 1 as its initial configuration. And what I've done here, V stands for valence, and that means what are we going to decide? What's the outcome of this? Now, we're doing a proof by contradiction. So I'm asserting that you have these 4 initial configurations. And the initial state, the initial configuration of each of them, is univalent. That is, it's guaranteed to decide one of these 2 values before any communication happens. I've ordered these 4 in an important way. Actually, according to, it's actually gray code order. So what we've got here is that the property that between each configuration, if we're going left to left, only 1 bit changes. So the valence is completely arbitrary. I could have chosen any digit here, it's unimportant. But the ordering of the initial configuration isn't. I'll show you why. I can explain why now. The main thing is that there's only 1 process that has a different initial configuration as you go left to left. But for example, these 2 configurations differ only at 1 level, but their valencies are different. So configuration 00 thinks it's always going to decide 1. Configuration 01 thinks it's always going to decide 0. And we also have over here another kind of pair of configurations that also differ at only 1 node, but their valencies differ. These 2 in the middle, C01 and 11, they differ by 1 node, but their valencies are the same. So they're actually uninteresting to us. You can probably see with a you can always find some pair of nodes where their valency is different next to each other. The reason you can do that is because 0 and 1 must both be represented in the initial configuration. If we didn't, we'd be violating this idea of validity, which is that you've got to be able to choose both possible outcomes based on the set of initial configuration. Given that 1 and 0 must appear in these configurations somewhere, well, 2 of these configurations are going to be next to each other, and they're going to be different in their valency. That's just guaranteed. We are going to exploit that. So, what does it mean to be 1 valent, univalent, 1 valent initial configuration? All executions of the protocol, no matter how the protocol runs, no matter how the network chooses to order messages, we're going to get to this I decided 1 box. And the same is true of C01. All executions of the protocol, no matter what set of messages we order, we're going to get to a I decided 0 state. Now, the reason that we chose them to only have 1 process different between each other is, well, consider what happens if process 1, which is the one where they differ in their initial configuration, consider what happens if that, that fails. I need you to consider it. I'm considering it. Okay. So if process 1 fails, the initial configuration, the non-failed processes, which are the only ones that do anything useful, they're completely the same. From the protocol's perspective, well, why would I send any different messages in configuration 00 than I would in configuration 01? As far as I can tell, the messages, the configuration is the same. I see 0 in process 0. So I'm only going to send messages that are consistent with that initial configuration. And this leads us to a contradiction. That means that the same execution is possible from C00 as it is from C01. Because to the protocol, These are the same configuration. First process failed. But we asserted earlier that these are univalent states. And so C00 is always going to decide 1. But C01 is always going to decide 0, but they're doing the same thing. They're sending the same messages. The processes are deterministic. When they get the same message, they're going to do the same thing in response. So that leads us to a contradiction. You can't possibly have this situation where all initial configurations are univalent. Because in step 2, we've shown that they'll actually get 2 configurations that are going to decide different things, which just contradicts our notion of what it means to be a computer. So, to conclude, this is what you take away from that right now. Every single protocol, I don't care, Paxos, Zero, anything, has an undecided bivalent initial state. And actually, this isn't too surprising. We really didn't think that we would just wind up all the nodes, set their initial configurations, and say, okay, off you go. It doesn't matter what happens in the network now. Messages can get sent, can get lost, doesn't matter, I don't care. I will always decide the same thing. It seems unlikely. You still have to prove it, but to me, this is not counterintuitive. However, it's important to note the key role that failure plays in that proof. So, without it, the argument doesn't hold. It's only failure that made those initial configurations look the same to the protocol. Okay, number 3. I tried to be slightly more pithy than the 4-line definition we've got here. I don't think that was difficult. The general idea here is that given an undecided state, a bivalent state, there's some way of always winding up in another bivalent state as a result. And you can kind of see, remember our proof sketch, you stitch these things together, these undecided states together, well, you just go around forever. So if we can always show that one undecided state can lead to another undecided state, then we can just deductively say, well, that just goes on forever. It doesn't matter what proof we're doing. We're going to wind up indecisive. We're not going to find it. This is a tricky lemma. There's no doubt about it. There are 13 details. They really are time. I will gloss over a couple of slides, but please tell me if you don't go through them in detail. I don't quite know where the after is right now for algebra involved code. I'll start with diagram. So here's the general setup. We start with a bivalent configuration, one where we're undecided. And we send some message from the equivalence configuration C, right? And some message E gets sent. That's the next thing it does in that configuration. You send a message E. And then E gets delayed. We have this set of configurations where E hasn't been delayed. Remember, the network can just delay a message as long as it likes, as long as it is eventually delayed. So E gets delayed, and we want to insert it. Other messages get sent to C. And then you say, okay, we'll consider the set of configurations where E arrives last. So we go through these E not delivered configurations, and we find that the last thing that happens is E shows up, and we say, let's set up configuration. What we're going to show, we're going to call this E arrived last set D, because E arrived last is nothing. One of these configurations, D, must be bivalent. And this is sufficient. This is our proof. It's only a bivalent configuration. Send some message, take some steps, and do some work, think about life, wind up in an undecided configuration. Then I can just take that undecided configuration, start there, and do the whole process over again. Go on forever. So, how do we do this? Well, from there, the proof is really about enumerating possibilities and showing that each possibility leads to a contradiction. First thing, the only thing really that we want to show is one of those states in D is bivalent. The first possibility we can consider is that D has a bivalent configuration. And if that were true, well, that'd be nice. You sort of go home, we've done. We have to consider the other possibility. Show that, well, if actually there aren't any bivalent states in U, we have to show that that leads to a contradiction. This is classic proof by contradiction stuff. Hypothesize that no states are bivalent, show that there's a contradiction. Perfect. We achieve this step first by showing that if there aren't bivalent steps, then there must be both kinds of univalent configuration in U. If we show that, we'll then show that this leads to a contradiction. Stay with me. What we're first going to do is show that D has to have a zero-valent configuration. And remember, this is our building block. We're going to show that D contains a zero-valent configuration, a one-valent configuration, and that leads to a contradiction. And that if it contains both of those things, it must also contain a bivalent configuration. So, first thing that happens is our initial configuration C. Well, actually, let me set the stage. Because C is bivalent, it must be able to get to a zero-valent and a one-valent configuration at some point. That's what bivalent means. At some point, I can decide one or the other. So let's consider how you get to decide zero. There's two possibilities. One is that C gets to this zero-valent configuration, i.e. it's made the decision, it's just not finished execution of the algorithm yet. It's made that decision before receiving that message E. When that message E, it's the last thing that happens before you wind up in the set of configuration. Then what happens is you get E, you wind up in this zero-valent configuration in D. Must be, right? Because you've got a zero-valent configuration here. You can't undecide, you decided it. So the next, no matter what message you receive, stay zero-valent. So this is one way that we get to a zero-valent configuration. The second way is actually we wind up in this zero-valent configuration after receiving this message. So C starts, does some computation, E is received, we get into set of configuration 3. And then we wind up at a zero-valent state. But remember, by our hypothesis that we're going to disprove, there are no bivalent configurations in D. Every configuration in this set D, the set you get after receiving D, must have decided one way or the other. So, if the alternate state is zero-valent, then D must contain a zero-valent state. So what we've shown here is that D must contain a zero-valent state. And if you take away nothing from the proof, other than that, that's what we show. Now, it's also easy to show that you can just substitute 0 with 1. And the same argument holds. I'm not going to bore you with the same slides with minus substitution. So, as a result of this argument, we can show that both zero-valent and one-valent states exist in D. But remember, by hypothesis, only those kinds of configurations. No bivalent configuration. By the time we get to D, the decision has been made. Now for the contradiction. I'm going to make it sound like a magic trick, but actually it's right. So, oh wait, two buttons to get all the things. I'm glossing over this a little bit. Believe me when I say there must be two configurations, we call them C0 and C1, that are separated by a single message M, where receiving E in either C0 or C1 moves the configuration to the univalent state of D. So I think I'm going to try and skip this on board. That's a permanent marker. To dry erase now. So what I'm actually saying here. Start off in C0. That's a configuration. And then we've got this guy, C1. Here. Okay? getting from C0 to C1 takes one message. M. Then, receiving E in C0 gets us to C0. And receiving E from C1, actually not relevant. Gets you to D1. Okay, so here's when these states are both in D, i.e. the set of invariant states that we talked about, you get to, because remember, the last thing we did was receive this message. There's nothing special about the invariant, it's just a distinguished message. You can say, he exists. Okay. So we're going to write that receipt of a message, kind of using terminology a little bit as some say CI plus D gets you to D that. That's the resulting state. So for example, C0 plus the receipt of the message M gets you to state C1. You can see that in the diagram. And similarly, C0 plus M plus E gets you to D1. You state where you are only going to decide one, and it lives in D. And we can say, again, looking at topology on the board, I'm sorry if you can't see it too well with that. I don't know how much clearer it's making it. C0 plus this receiving message E gets you to D0. So remember, E always winds you up in the set of invariant invariants. Again, just keep in mind what we're trying to prove. That actually, there's some bivalent invariation. Yeah. Yes. E is. If you think of it as a group of messages, it's the last message received. Okay. Now, it's where it does get a little hairy, and you can move quickly through this. Messages have destinations. M goes to a destination process. E goes to a destination process. The lemma that I didn't describe in the paper is lemma 1, which says if messages go to a different process, it doesn't matter what order they get received in. You wind up in the same ultimate configuration. That is, they commute. So remember that we have C0, receiving M, receiving E gets you to D1, this configuration. It's also true, by this commutativity rule, that C0 plus receiving E, which should get you to D0, if you look at the chart, is the same. So C0, receiving E and receiving M is the same as receiving M in D0. But by commutativity, that's the same as getting you to D1. And that leads to a contradiction. Because we said that D0 is 0 there. You can only decide 0. But D1 is 1 there. You can only decide 1. Well, that's bloody confusing. It's a contradiction. If M and E go to different processes, that leads to a contradiction. And that kind of pops the stack. Think of it as an exception thrown deep inside the proof. Pops it all the way up the stack. And we say, oh, okay, D0 and D1 can't be univalent if M and E go to different processes. There's another consideration, unfortunately. Consider that E and M might actually go to the same process. The lemma about commutativity, i.e. the order in which you receive messages not matching, that doesn't apply here. They go to the same process. And the way we get there is to say, okay, well, let's consider some deciding computation. The run of events and run of messages from the original state, C0 at the top there, the original bivalent state, the undecided original state, where some process, the one that's going to receive E and M, does nothing. It looks like it failed. So here's failure rearing its ugly head. To get to D0 and D1, univalent states that you keep banging on about, only E and M are received. Only P took any steps to get there. Again, for the diagram, the only messages we're talking about here are M and E. And to get there, only P, the process that we're saying failed, actually received it. That's what we're asserting here. So in that case, well, by the same argument we had in the previous lemma, where if a process fails, you can do the same thing for different iterations where that process is in a different state. This deciding computation that winds up in a deciding state can apply to both D0 and D1. We're very nearly there. So, by assertion, D0 and D1, they're both univalent, because remember, if they were bivalent, you had a contradiction, and then you'd be done. And they're a bit. D0 plus this deciding run must get into a zero-valent state. D1 plus this deciding run must get into a one-valent state. Now, take it from me at this point. I was trying my hardest, by the way, to spell prove. I almost got that. So, yeah, probably needs to prove is an argument. But by a bit of manipulation, we can show that down here, these last two lines, starting in our initial configuration C, doing this run, this deciding run R, is going to get us to some state, and then receiving another message or two. And this process that failed and then maybe came back to life means that you can actually wind up either in D1 or D0. But that contradicts our assumption that this run R is a deciding run. It can't have decided because the property of having decided means that you don't change your mind. You actually stick to that. So this actually, I'm sorry to be ending kind of with a wink rather than a bang with it, but this is the big sort of no matter where these messages M and E go, they lead to a contradiction. D0 and D1 can't both be univalent without there being bivalent states in D. Remember, having bivalent states in D, undecided states, is what we need to make this stick. The consensus protocol never terminates if there are, or sorry, may never terminate if there are bivalent states in D. Now, you thought this was heavy. I agree it is. This is how I originally wrote it out. It actually made me more readable, but it's possible to present. So that's enough. So that's the proof. That's the end of the algebra. That's the end of the heavy stuff. I just want to talk quickly, because I've talked for a while now, about what the consequences are to this discovery. Now, I can't do them all justice. Today, a deep result with practical and theoretical implications. The first people I should go to is actually the paper themselves, and I like this quote. They had this wonderful humility. They say, you know, what we just showed is what the problem for database architecture is actually possible to solve it. But they acknowledge immediately that it doesn't actually mean you can't use consensus in your distributed systems, which is good, because we are. What they actually argue, what Fischer, Lynch and Patterson argue, they say, well, okay, look, we've shown something to be impossible, but we kind of know that we're using it. So maybe there's something wrong about our system model. Maybe we actually need to refine how we model distributed systems. I'm not sure, I mean, there have been a number of efforts to remodel distributed systems and do different things. I'm not sure they've gained a huge amount of traction. This asynchronous network with zero timing guarantees turns out to be quite realistic when you're talking about distributed systems with massive active distribution and therefore very high latencies, hard to synchronize clocks and all that stuff. And you can idea how realistic that is. I mean, Google, like the Spanner paper, they actually go and deploy hardware in their data centers to synchronize clocks because it's that important to them. Without that specialized hardware, it's actually very difficult to synchronize clocks accurately. This asynchronous assumption we had at the beginning turns out to be more accurate than credible. I love this at the end. Maybe terminations only require the probability 1. Okay. That's actually a subtle, I guess, theoretical point. Probability 1 is not the same as an absolute guarantee because you do not know how long you're going to be waiting for your execution to actually fail. Other consequences, so Paxos, as we spent an hour banging on about why consensus is solvable, but both over Paxos and mass consensus. Paxos is actually really weak. The algorithm of Paxos itself is not so obviously vulnerable to these kind of consensus problems. What Paxos does is it cleverly says, I'm going to work brilliantly if you get legal action perfect. Which is great, but as we discovered, perfect legal action, wrongly running your Paxos protocol, it's solvable if and only if the consensus is. That's an impossible thing to do. So what we actually do with Paxos is we suffer the possibility where there may be more than one leader elected at any time to run the Paxos instance, but those instances may conflict to many other terms. We have this possibility with Paxos of a lack of termination. There's also this nice kind of theoretical reaction into randomized consensus, which I kind of alluded to before. Technical impossibility is only interesting if its probability is not like vanishingly small. This idea of randomized consensus gives an example of this algorithm that they alluded to in the FLP paper. By Ben Orr, give an algorithm of termination probability 1, but the rate of doing that actually is quite high. It's not a particularly efficient protocol in practice. And there's also a lovely strain of theoretical visual systems dealing with this idea of failure detectors. I.e., we showed that if you can't detect if the machines fail, you can't do consensus. Well, what does it mean to detect if the machines fail? How strong a guarantee do you need before you flip that switch and consensus becomes solvable again? It turns out that there is a really deep connection between just how you do failure detection and whether or not consensus is solvable. Yes, exactly. Like running like an oracle, and that's exactly right. So, say we hypothesize the existence of the system that we say this machine is definitely dead, well, we can solve consensus, it turns out. If another machine says this machine is probably dead, but I'm not sure, but we'll pretend like it is that strong enough to solve consensus? Do you actually run into any problems? There's a lovely paper talking about the weakest failure to solve consensus, and that actually characterizes just how strong a guarantee you need before consensus becomes solvable. There's also the battle of the three-letter acronyms, FLP versus CAT. The theorems answer one thing. They are not the same thing. I have been extremely wrong about this in public. FLP and CAT are not the same thing. Sloppily and without much careful thought, asserted that there were ones in a public place, and got an academic kicking where something like hung up. And I thought about it hard, and actually I was really glad that it led me to show that, to my satisfaction at least, that FLP and CAT are not the same thing. FLP is stronger, in my opinion, because the hierarchy of failure models, CAT lives kind of in the middle. You actually need quite a complex set of failure models. FLP, the only kind of failure that it needs is a machine stops. Yes?
So, okay, that's fine. They're not the same. But since you're an expert in these things, can you help next time? Does FLP apply some or all of CAT?
I believe, I don't want to, this is where I get, this is where I make mistakes, making assumptions, but like that. Okay, well, I happily this guy. One is, I believe, strictly stronger than the other. I believe that a solution to CAT solves the FLP problem, but it's not true the other way around. So if you solve FLP, you do not solve CAT. My theorem about CAT, actually, is kind of odd. It's extremely easy, if you think about it, to prove. You have this idea of consistency and the possibility of never communicating between two halves of the network. Well, it seems self-evident you can't have both of those sides of the network remain consistent. So, and actually, that blog post, by the way, does a more precise job of connecting the two, a more precise one, right? Bit of further reading, I don't want to go through all of these, but these are some of the papers that I think I focus on kind of the theoretical ones. Lynch went and then talked about 100 different possibilities for distribution. That's kind of cool. The weakest failure detector I spoke about. Sharing memory and message passing, that shows the relationship between shared memory systems and message passing systems and what you can do in one and the other. That's very interesting. Weight-free synchronization talks about consensus in shared memory systems, which is a very related but different kind of problem. And then the final paper is the one that talks about randomized consensus. And finally, after 72 slides and your very kind attention, I have something about excellent quality. That's all. So questions? Wow.
Yeah.
Yeah, please.
It's all a bit theoretically, but since your work at Cloudera, can you speak to that some of the very specific pieces where consequently there's a big minor
the answer is no, actually. I hypothesize you all, but we don't do much consensus protocol. Really, the design or implementation. I think what's key about this result is, like CAP, you know you're going to give up one of two things. You're either not going to be correct or you're not going to finish. The key is making sure, unless you're really sure you can understand it, you don't finish. Being incorrect can be deathly. There's imagine a transactional commit system where you vote to commit, but the consensus protocol is wrong. So somebody says yes, somebody says no, but you wind up committing to one of them and not to the other. So that's a really bad situation. It's often hard to say. But practically speaking, you really want to give up life. And the answer is, for the kind of software that we work with, I mean, it's led to me that distributed systems implementation is so inconclusive. It's only really, honestly, that we've researched in the last 10 years. We're still kind of neophytes as an industry about implementing these things at 1,000 nodes here. Your system will break in other interesting ways before your consensus protocol gives up, typically. But I would say that it is not a good idea usually just to every time. The one place that we did wind up implementing the consensus protocol was for replication in the HDFS name. So, you know what to do. The name node is the stores the metadata of the file system, where the box is located. In a single point of failure for the longest time, guy could use very high quality engineer. Designed and implemented a consensus protocol to do that. And he wound up, he put through tens of thousands of hours of machine testing before he was even satisfied with what consensus. So, I don't have great anecdotes. I don't have stories of my consensus protocol failing to terminate and apply for my job. But I think it really, this acts more as a cautionary tale. Something to be prepared for. So when you design the systems, okay, what happens if something goes inside? What's our failure mode there? How do you recover? If it's vanishingly small in probability, you may still hit it, but if you have a human-based intervention mechanism, that's completely wrong. This result does not apply to humans. So, yeah, that's my kind of lack of war stories. Looking back, that's a really good question. I'm not aware of a generalized mechanism for the question whether it comes off and through the camera is, okay, so I've got two consensus protocols. How do I evaluate their failing? Good ones will allow you to analyze them. What Paxos does and say it's not up to me, it's up to the legal election protocol. And you may be able to design legal election protocols that actually you can reason about quite formally. But I'm not aware of a general mechanism saying, here is my likelihood of hitting this state, here is my likelihood of hitting state 1 is bigger. But apparently, yes. Asking for references.
So what is it? It's like so you set up what, like the proof for each one of them, and see if you can actually reason your way into whether the proof no longer, or that you just like hit some.
You hope someone else is not there.
Okay. Yeah.
There's a reason there are only a few consensus protocols. Partly because actually it's now a well-studied problem. It has established solutions. And you look at Raft, and it's really only improving upon practice in the sense that it's probably easier to implement, having particularly profound theoretical properties.
So whatever somebody's PhD thesis is the thing that we're eventually going to.
Exactly.
One of the things I want to throw in there too, why you pick up access a lot and why it's kind of like still training a lot of these other consensus protocols in the group is that you can just prove that it's all consensus because
it's a very good point. So yeah, Lamport had this code on practice where he said, in a synchronous network, you have this many round trips, and you cannot be consensus better than that. And oh look, Patches achieves this bound. I think you're right. I think that's one of the reasons Patches did that. Although Patches has this incredible story of history about Lamport wrote about something to a bunch of people, submitted it for a publication, and got lost in the filing cabinet, or left in the filing cabinet for a while. And Lamport, in a way, obviously is the most brilliant theoretician, but he's also kind of a grunt, as far as I can tell. There's this little paragraph about how no one really understood it. And, nobody really appreciated the true genius. It took a while before someone who wrote and said, oh, okay, this is solving an interesting problem. It's actually all about let's get it published. And then he published this great paper called Patches Made Simple. Which is
obvious.
Yes. I actually would contend that Paxos isn't that horrible to understand. I mean, it requires careful study, but it is not as monstrously hard as everybody makes. A great number of people make it up to it. Implementing and getting it right is, and Google had a really good paper on how they had to do that and how they did it. The other thing that Paxos had, the proof really carried a lot of weight. So we're taught by Mike Burrows, who is the guy at Google who wrote the Chubby system. Apparently kind of turned up and wrote Chubby in 3 days. And I think they then kind of made it, then they introduced Paxos and made it a better rounded component of the system that you saw in the he said, yeah, there's 2 kinds of protocols. There are Paxos, and then there are the broken ones. And that's, to a first approximation, that was kind of true at the time. There was this thing called U-stack replication, which is another protocol which is actually not the same as Paxos, quite similar, and it was also correct. Since then, we had ZAB. That actually requires a stronger network model than Paxos does, because messages can't get reordered. They require TCP, which works fine, frankly, but it's not as powerful an algorithm as Paxos. Now we have Raft, which honestly I think kind of really strengthens the but I know there are people who do it. Another question, yeah.
It's not exactly a question.
Yeah.
So, and I think that we ended this one. The question was, you said something like
right.
The reason that word might was used is it wasn't saying that we allow it.
Right.
It says that that's a fundamental part of the problem. It's like if you capture every time somebody solves that, they give up. You can't give up that you have competition.
Yeah, absolutely.
And the reason I did this is that capture is a lot like consensus is a lot like permanent.
A lot like what?
Just like permanent.
Okay.
In the sense that they say you can't stop playing.
Okay.
Yeah. There's no, it doesn't draw a line around consensus that oh, well, I use consensus as a service and I have to.
Right.
Well, the correctness of your application depends on that you decide on.
Yes.
So,
very good.
I'll throw out an example here. Right? There's certain companies that already might want to have a job at well, not Google, but you heard about them using consensus for a while. And I interviewed them.
Me, Cloudera.
And
Okay.
And in the process of my interview, I did a job, because I demonstrated mathematically that the way that you consume computer, giving up the consistency.
And it seems like a dumb way to use it.
So it's like, it's kind of like you look at database, right? You ask for the state of things once the transaction connects. They'll still only validate that data. So it's like, if you think you saw a gap where you built a consensus service that's correct, and then you see that, you say, you pretty much have to look at the problem inside of that.
You make a number of different points in the event together. You have to view your distributed system holistically. Every actor in that distributed system is part of the distributed system. And the way they interact is part of the workflow. So again, Paxos does a pretty good job of establishing what it means to learn a result, which I like. This curmudgeonly example is he does have some really good ideas. So has this distinguished idea of learners in the system, and they participate. They are informed, and the way that they receive messages is carefully defined. And that does exactly what you say. It brings everybody into the consensus. So yeah, I can really use consensus. Although I can't substantiate your assertion of that. That's how I know. Do you? So, great question. You could also look at Byzantine portfolio. So Byzantine governance problem is interesting. It's written by Landlord. It's working. They actually talk about numbers and packing them out and doing stuff. That's kind of fun. My caution against thinking too hard about Byzantine portfolios is that it's profoundly impractical. There's lots and lots of work done on implementing and improving the solutions that we now have, but none of them actually are good. No one is running good. I think you can go one of two ways. You can decide if you don't know about practice, I want to go and understand practice. So I'm going to be a huge bibliography. I have not about practice on my side, actually. So access. It's a bibliography of the If you want to say theoretical, I like reading this very effective. I think that's really cool. It does require, it's not easy. I mean, it's one of those papers that you and then you go away from it up to 6 months, and then you kind of up to 6 pages. But it's still really good. And go to Alex next.
The risk of stepping on the speaker code. I actually think the draft paper is worth reading because it is much more understandable.
That's a really good point. I don't need to dismiss that as very pedagogical.
Yes, pedagogical, or at least I don't know, like that's just kind of pronunciation.
Okay. I mean, anyone else here? No, okay, so it's pedagogical. Yeah, as a teaching thing, it's really good. It is good. It is worth reading. As a theoretical contribution, I think there's less to it than it's given for. And there's a bit of like a kerfuffle, like putting it into a major system conference and actually hasn't told us much. But it is a very practical. It's hard not to do. So in practice, here are the things I have to think about. The stuff that actually difficult. When do I write to bits? I didn't touch on any of that here. Like how do you solve? How do you deal with stuff like yourself?
I think that when we spoke with the consensus, it's very difficult. I know I started reading that. It's hard to understand how you kind of it's hard to understand how and more understand how to implement it. Someone's drafting policies, so I'm not sure that they're delivered. Understanding that it's correct. Right? Because you want to understand consensus, you want to understand the
yeah.
It's not clear to me that draft basically any more than access what it is that valid that's my goal. I'd love to talk to you guys about that afterwards because we told me that be able to paper. But the one thing I'm curious about, because brought up residential design, is the most recent work is in PLA Plus.
Yeah.
And I'm curious, I haven't done much with PLA Plus,
I don't think that when I read my PLA plus test, I'm not going to have like Java tests where I can test my distributed system yet. I wonder if you could, anyone, I don't know if anything, talk about, experiences with these normal stuff, these types of languages, what they really show, when the right time and to use them are, and what value they have.
So just to backtrack to your investigation, I actually, I think it's critical that the graph paper community is correct. So each convinces a set of people whose opinions I trust. Because otherwise, for all the nice implementation in the world, you don't know what they're putting out.
And those opinions are probably the only opinions that are actually like few levels or like a few steps ahead from mere mortals that actually have no fucking clue about the code.
That's true, yeah.
So if they can't convince them, it's like there's not really hope for the rest of us. And this is cool.
On TLA Plus, I don't know if anyone's got lots of experience with it, please speak up. I know Amazon had a paper recently.
Yeah,
Oh yeah, very good.
so like,
Find it.
Right, it's much more head down.
so can you describe the process of like maybe setting something up on the LA process? Like you set like your assumptions and then you have like some sort of like mechanized way to prove it. Like I saw a presentation by Lamport like maybe 2 years ago and I forgot.
So you find it there.
Okay.
What I would do is each step is the lowest you
Uh-huh. Give you an example?
So, yeah, the virtual I specified was to wherever stops out there, you say, the sequence will send you messages will arrive in the service.
Mm-hmm. So can you say the states that you are expecting to arrive and then just actually have TLA help you along the way to know if they're valid or not? Is that the power of it or what?
Yeah, so this is a essentially you're going to write down something like the first order line. Essentially, the invariance of the whole. So they always an initial state, but then you transition to that initial and the other state is always an invariance. The nice about TLA is compared to things like alpha and other cases that lets you pick one of two measures, but you want to do a sort of machine assisted, human assisted use, where in the end of that is really the invariance can never be violated. Or something that's not more practical that I think I'm trying to do for more readily is actually run it through a model factor and do a sort of bounded test. All the states of the system could be lost in that. That could be a very hard to violate in many methods. What they encourage you to do is do model checking first as you enrich your set of variants or your descriptive system. And the end goal is some sort of actual formal which is variance.
Yeah.
So the variance you talk about mathematically actually what primarily about saying. Right, and that's exactly what we
And so yeah, a line is function. You get a model that's defined coverage. You say that's thing. I said that's a never receive. Your next people never receive. But the human assisted proof that existence of the proof line is fine. Part of the problem is because it's kind of a black art, and black is popular among because of the fact. It's very difficult to take something you can express and feel like you express proof and actually implement. There's always something you can do.
What would you need to? Oh, because you have like you have an assumption of a protocol, and then like you check it with TLA, and then actually eventually you have to translate it into something that actually fucking works.
Or more often, it's the other way around. It's C++ program.
Oh,
and
whatever.
you're running in production, and then you're trying to back that proof.
And that's the problem with the proof in one way. It's very hard when you can't see general purpose code and TLA. So what ends up happening is you develop an initial model, you tell yourself, I'm not going to innovate on this diagram, I'm not going to rewrite it. And then you implement it. Which is just very difficult. It's kind of a non-starter for a lot of people. And the other thing is that it's almost impossible to express the whole application. Kind of like what you said, where you can't draw a line around consensus. You can do this proof of the full protocol and then choose this. But the way that you consume it I mean, it's one of those things that it has a limited validity. Kind of like, how many people your program has? Okay, so you'll know this. Never put up. Well, right? But the reason I say this is that, you know, if you have a deep understanding of why monads are happening, we're missing a distributed monad. You know, monads, for people that don't know, it's this thing where Haskell describes this perfect space where your program is perfect. But it's completely useless until you can say, when it executes, you think that's it. This IO is done. This is how it breaks the Haskell code. And you don't have that for consensus. You don't have that for distributed systems where we can say this abstraction, this distributed monad, takes the output of consensus and interfaces it with the world. Turns out that's always a property of your application. It's always one off. And it's why RAP is useful, because it tries to answer that.
We should talk about that because I think it ends up being dividing for talking to
I
yeah.
How do you have to meet your studies for basic order to use